I'm in the position of the starboard gunner. He's got this control arm sticking out here, which fits under the right armpit. His right hand then goes forward to this pistol grip arrangement under here, and then he sets his eye to the telescope here. And now, using his body weight, he can elevate and depress the gun, and even, to some extent, swing it round to track a target. The gun will fire out to about 7,000 yards. In fact, at anything more than 1,000, you'd be lucky to see anything, never mind hit it. Don't forget that the gunner can't see anything else, only what's through his telescope. So he's virtually got to be directed into whereabouts in his arc the target is in the first place.
If the tank was to improve, the whole process of aiming and firing needed to be speeded up. The breakthrough came from the war at sea rather than the war on land. The British Royal Navy had used an optical system to calculate range for some time. It helped their gunners hit targets many miles away. But the range-finding equipment was big and heavy, not easy to fit into a turret. It wasn't till towards the end of the Second World War that this optical range-finding technology was made compact enough. Two lenses were positioned on either side of the turret. Each lens was connected to the same eyepiece by prisms. As the distance between lenses is known, the distance to the target is calculated using trigonometry. The gunner sees two images, one from the left, one from the right. Turning a hand crank pivots the lenses on either side till the images line up and merge. Better optics and rangefinders meant tanks could hit targets at far greater distances. This encouraged tank designers to fit much bigger guns with more power. One of the most feared tanks of the Second World War was the German Tiger, with the most powerful gun yet mounted on a tank.
It's an 88mm high-velocity gun that was originally designed for anti-aircraft work, and the British had already come to dread it in the desert. The Germans had enough flexibility in their system to convert their anti-aircraft guns into the anti-tank role. With a gun like that, the sort of accuracy and hitting power it's got, you could take out other tanks at ranges where they cannot effectively take you out in return. That's its real asset, that big gun.
Even as it destroyed everything it came across, the Tiger had one weakness. It couldn't fire its gun on the move. The gun's powerful recoil would have seriously damaged the turret unless the tank was stationary. The tank's crew had to halt, swing the turret, unlock and elevate, aim, then fire. By the time they'd done all this, they might have lost the advantage of their big gun and become a target themselves. Even tanks with smaller guns couldn't fire accurately on the move simply because their barrels bounced around so much. Engineers had to come up with a mechanism that would keep the barrel steady, however rough the terrain. They began with this, a gyroscope. A gyroscope is a spinning wheel on an axle. Once spinning, it resists changes to its direction due to the forces created by the fast rotation of the wheel. If a spinning gyroscope is put into an environment that rolls around, it'll remain stable. Connect the gyro to the controls that position the gun, and the gun remains locked to the gyro. It's totally stabilized. The gyros in an Abrams tank keep the gun barrel steady, even as the tank crosses the roughest terrain. By fitting further gyros, it's possible to keep the gun locked on target so it can fire on the move with accuracy. Now the tank had an accurate and powerful gun that could fire on the move, designers could turn their attention to what it fired, its ammunition. During the Second World War, designers came up with an ever-growing arsenal of deadly weapons. One of these was known as the squash head. To kill a tank crew, it doesn't even have to get through the armour. To demonstrate the deadly nature of this weapon, we've asked chemist and explosives designer Sidney Alford to set up an experiment.
So here we have 150 grams of plastic explosive.
Sidney has welded steel armour to a metal plate and bolted this in place on the side of a mock-up turret.
I'm going to plonk it onto that target, thus.
His challenge, to destroy the inside of the turret without penetrating the armour.
I'll plonk it a bit more.
This plastic explosive he's patting into place will replicate the behaviour of the real squash head.
That now represents the explosive which has arrived inside a shell which has squashed itself against the target. I'll take the detonator.
Inserting the detonator turns the harmless, inert putty into a lethal explosive that could blow most of the roof off a house. There's a melon sitting in for the crew.
Goodbye, melon. That's it, right? Firing! 4, 3, 2, 1. Ah, here we are.
At first glance, it looks as though Sidney's squash head has failed to do its work.
But if you look round the back of the plate, I think I see one former melon, which is no more. And here, still warm. You would not like to share the inside of a tank with this travelling at, I would guess, roughly the speed of sound.
This scab of steel has been blasted off the inside of the armour.
What I'll do now is unbolt this and we can have a good look. There we are.
The squash head shell looks like any other as it leaves the gun tube. On impact with the turret, it sticks to the surface like a cowpat. The shock waves from the explosive cause little damage on the outside, but devastation on the inside.